Okay, the next couple of videos I'm going to talk about concavity and the second derivative test. But first of all, let's talk about concavity. What is concavity? Well, concavity is actually the direction of the curvature for a graph. If a graph is concave upward, it's actually bending counterclockwise as you move left to right. So if you look at this function here, notice that the graph actually has sort of a counterclockwise bend here to it. Okay, so that's a counterclockwise bend. And this graph, even though this function is increasing and this one's decreasing, they're both concave up. Because if you look at this graph, it actually has the same counterclockwise bend to it. So concave down actually has a clockwise bend to it. So here's a graph that's increasing, that's concave down, so it's kind of bending in a clockwise fashion. And this function is decreasing and it's concave down, so this function is actually decreasing and concave down. I know technically this function over here is decreasing, but I was talking about this portion is increasing. So here it's increasing in concave down, and then over here it's actually decreasing concave down. So anyway, so you can't relate concavity with increasing and decreasing, because a function can be concave up and increasing and concave up and decreasing, or it can be concave down and increasing, or concave down and decreasing. So let's see if we can figure out how to determine concavity. Now, where a graph changes from concave down to concave up, where a graph changes from concave down to concave up, or vice versa, is actually called a point of inflection. So this would be called a point of inflection or inflection point. Now let's see if we can find the inflection point below. Now I actually gave it to you so you could see it, but if you look at this graph, as you go from here to somewhere over here, you've got that clockwise curvature. So actually over here the graph is concave down, and then somewhere in here, so I went ahead and labeled the point right here. At this point it actually changes from a downward concavity to an upward concavity, so it's bending upward. Now over here you've got this graph is concave up on this side, so it's concave up over here, but once it crosses this point it switches back to concave down. So this would be called a point of inflection, and so would this. These would be called points of inflection, where the concavity changes from concave down to concave up, or concave up to concave down. Okay, now the definition of concavity, it's a little strange, but let me give it to you. It says, let f be a differentiable function over some interval I. The graph is concave upward if f prime is increasing. Now remember, f prime is the first derivative. So basically, now it's not saying f prime is positive, it's saying f prime is increasing. So a graph is concave up when f prime is increasing. And likewise, a graph is concave downward, it's concave downward if f prime is decreasing. So basically, if we can find where f prime, the first derivative, is increasing or the first derivative is decreasing on an interval, then we can determine concavity. Well, here's something, it's kind of difficult for students to follow, but I want you to think about something here. F prime is a function, correct? Now remember, we learned that a function is increasing when its derivative is positive. But in this case, the function is f prime. So f prime would be increasing if its derivative is positive. But what is the derivative of f prime? It would be f double prime. So in other words, f prime is increasing when the second derivative is positive. So if you put all that together, basically to determine where the graph is concave upward, all we have to do is find where the second derivative is positive. Because if the second derivative is positive, that means the first derivative is increasing, and if the first derivative is increasing, then the graph is concave upward. Now, likewise, if it's concave downward, the first derivative is decreasing. Now, when is the first derivative decreasing? Well, when its derivative is negative. So if the second derivative is negative, then that means the first derivative must be decreasing, therefore the graph must be concave downward. Now you can see this in the pictures here. Let me show you some examples. Now remember, this piece of the graph was concave down. So look at these 3 points as I move left to right. Notice this point, look at the tangent line. It's a steep tangent line, so maybe like 10. Now then up here the tangent line is not as steep, so the actual tangent line is a smaller number. And then over here the tangent line is actually negative. So basically what you're seeing here is that the tangent line, the slopes of the tangent lines are decreasing. So that would mean that the first derivative is decreasing. So when a graph is concave down, then the first derivative would be decreasing, and therefore the second derivative must be negative. Now likewise, if you looked here where it's concave up, if you looked at some points here, your tangent line here would be something like this, and then when you move down here, your tangent line, it would actually increase, the slope would increase, and then when you get over here, you would actually get a more of an increase. So as you move left to right on this piece of the graph, the slopes of the tangent lines are increasing, so that means that the first derivative would be increasing, and if the first derivative is increasing, then the second derivative must be positive. So basically when you put it all together, if a function is the only way a function can be concave down is if the second derivative is negative, and the only way it can be concave up is if the second derivative is positive. And so that leads us to this test for concavity. So it says, let f be a function whose derivative exists on an open interval I. If the second derivative is positive for all x in the interval, then the function is concave upward on the interval. But if the second derivative is negative, then the function is actually concave downward on that interval. So again, I just showed you that, but so for this piece where it's concave down, the second derivative is going to be negative, and then over here the second derivative is actually going to be positive. And on this one we have concave up in here, so in here the second derivative is going to be positive, but over here where it's concave down, the second derivative is going to be negative. Now, to find these points of inflection, basically what we're looking for is where the second derivative can change from positive to negative or negative to positive. So to find that, we look for what we call possible points of inflection, because a point of inflection, a point C, f of C, is a point of inflection. In other words, if it is a point of inflection, then either the second derivative at C is 0 or the second derivative does not exist at C. So basically here for this one, if this is a point of inflection right here, if this point's a point of inflection, then that would mean the second derivative of this function at 1 must be 0. So that's what we'd have. And the same thing here, the second derivative here at 5 pi over 2 must be 0. Now there's also the case for when the second derivative is undefined. Let me just show you that. If you look at something like this, okay, so right in here it changes from concave up to concave down. Well, you get a vertical tangent line right here, so the first derivative would not be defined, therefore the second derivative would not be defined either. So here's a point where the second derivative would be undefined, but yet this would still be a point of inflection because the concavity changes from concave up to concave down. Okay, so basically we can discuss the concavity by looking at places where the derivative, the second derivative, is 0. Not the first derivative, but the second derivative. So let's take a look at this function. Now I'm going to assume here that you know how to find derivatives. So here's the function, here's the first derivative, and then from the first derivative we get the second derivative. And then we set the second derivative equal to 0 and solve for the zeros or roots. So here I get that minus 1 and 1 are the roots. Well, I'm going to set up a table kind of like I did with the first derivative test when I was looking for extrema, but now I'm studying concavity. So basically I'm breaking the x-axis up into intervals, and the place where I'm going to break it up at is at -1 and +1. So that gives me everything to the left of -1, and then everything between -1 and 1, and everything to the right of 1. And so just like before, I'm going to pick a test value in each of those intervals. But since I'm discussing concavity here, I'm actually going to evaluate the second derivative at this test value. So we're going to put -2 into the second derivative. So plug -2 into this derivative, and you'll see that you get a positive number. So since the second derivative is positive, remember when the second derivative is positive, the graph, the conclusion for the function is that the function is concave up. So the function would be concave up on the interval -∞ to -1. Now if you test the next interval, you test it with 0. So if you put 0 into the second derivative, you actually get a negative number. So that means that the graph is concave down on -1 to 1. And then for the third interval, if you plug 2 in, you'll find that the derivative at 2 is actually going to be a positive number, so the graph must be concave up here. So on the outer two intervals, the graph is concave up, and on the inner interval from -1 to 1, the graph is actually concave down. And you know, you can view the graph and see that if you want to. So you can go to a graphing website and go ahead and graph the function, and then identify the point where x is -1 and x is 1 on the graph, and notice that the graph changes concavity at those points. Okay, so here's another one. Again, find the first derivative and then find the second derivative, and if you set the second derivative equal to 0, on this one you're just going to get 1 0, -2/3. So basically what we're going to do is we're going to break the number line up at -2/3, or the x-axis at -2/3. So we're going to look at everything to the left of -2/3 and everything to the right of -2/3, and we want to see if the concavity changes. So I'm going to pick a test value over here of -1 and a test value over here of 0. Now when I plug -1 into the derivative, I actually get a positive value. So the second derivative is positive, so that means that f is concave up on this interval. And then over here, when I plug 0 in, I get a negative value. So f must be concave down on that value. So the graph f of x is concave down from -2/3 to infinity, and concave up from -∞ to -2/3. And again, if you go and graph this function, you should be able to identify the point where x is -2/3 on the graph, and you'll see that the graph changes from concave up to concave down at that point where x is -2/3. Now I don't know exactly what the graph will look like, but I do know from the calculus that we just did here that the concavity does change from concave up to concave down where x is -2/3. Now to get the y value, I have to plug -2/3 in. We'll do that on the next video. So I'll do some more examples of discussing concavity on the next video series.